So now we will take a look at more advanced settings where we will be mixing different types of constraints with different types of materials. So take a look at this example that I rendered. So here I have a metal wrecking ball hitting the wall from behind, and notice how we have two different types of materials here. The center or the core of the wall is made of concrete, and then we have a thinner, more soft material that it could be plaster or wood. It could even be gypsum, depending on your shot. The important thing here is that we have several different materials in one same simulation. So let's take a look at how this was made. So I have created here a very simple scene. So the only thing I have is a grid object to serve as a floor, a camera so we can take a look at the final angle, and then we have the geometry, which is just a simple box. So this will be the core wall geometry. I also created another very thin wall that will be the plaster. So if you take a look at this from above, they're not exactly touching each other. This small space will help with the collisions. And finally, we have a sphere that will be our projectile or the wrecking ball that will hit into the back of the wall. So let's first take care of the velocity of this sphere. I'm going to add a point velocity node to give the wrecking ball an initial velocity. So let me template both of these geometries. Probably take a look from the left side. So you can spacebar 4 to go into the left side. And I will quickly create here a marker. And I will call this marker V as in velocity and make the type to vector. So once we add the velocity, we'll be able to see the trajectory here. So on the point velocity node, click on the add velocity. So the wall is facing towards the right on Z. So let's make this velocity of 20 units. So it's 20 meters per second. And let's also change the Y velocity. Let's try with 1. Probably 2. And this would be the initial trajectory of the wrecking ball. So now we can turn off the visualizer. And one very important thing that you will want to do before bringing the geometry into the bullet solver is create a name attribute for each of the pieces. And this can be done with a name node. You can also use a wrangler for this, but it's easier with a name node. So press tab and type name, then press enter. And I will connect this name node to the first geometry, and I would call it wall. So both the name of the node and the name attribute here, I will call wall. And another thing that I like to do is change the color of these nodes, just to easily distinguish them among the rest of the nodes. So I will Alt and drag this node just to copy it, connect it to the second geometry, which is a plaster geometry. And of course I would change the name to plaster. Also change the name of the node. And I will do the same thing for the wrecking ball. So this will be the wrecking ball material. And now we are ready to bring the geometry into the solver. So we can select all the nodes and merge them together. And for now, let's just make a quick solve. So lay down on RBD bullet solver. Let's just connect this into the solver. Activate the bullet solver, and let's create a ground plane just so they don't fall into infinity. And let's press play. So this is working fine. Let me turn on the real-time toggle. So the wrecking ball has an initial velocity, then hits the wall, and the wall will just fall down, just as expected. So first of all, let's take care of the connection between the wall and the plaster. And for that, there's a very useful node called RBD, constraint from rules. So I will lay down a node, and I will connect it between the merge and the RBD bullet solver. So real quick, I will change the color. I also changed the color of the RBD bullet solver. And let's take a look at the properties of the RBD constraint from rules. So what this node will do is look for the different named pieces and will attempt to connect them together with a new constraint. So let me go into wireframe mode so you can take a look at this. Let me select the RBD constraint node. And you will notice that here is a new piece or a new constraint that has been created between these two. So if you take a look from above, you will notice that here there's one single connection that would serve as a constraint between both pieces. And this connection has been determined by finding the pieces with different name at a certain search radius. So you could also change the maximum connections. In this case, the defaults will work fine for this scene. Just one thing that I recommend is to turn on the group name attribute, because maybe in the end you will have different constraints and you may want to configure the constraints differently. So let's start doing that. Let's lay down an RBD constraint properties node. And of course, this node will let us change all these attributes. So connect the RBD constraint properties just after the constraint from rules. Make sure to connect the second input to this node, as well as to the RBD bullet solver. So in the RBD constraint properties, make sure that the constraint group is connections. So if you don't remember the name of the group, you can go back to the RBD constraint from rules. You can copy this name and paste it here. So whatever changes we do on this node will only affect this group of constraints. So let's also change the color of the constraint to a bright yellow so we can distinguish them later. For now, let's increase the strength and let's try simulating this. So you'll notice how the plaster won't come apart from the wall. So let's now start fracturing the wall to create the destruction. So I will make some space just below the RBD constraint from rules. I may also want to change the color of the RBD constraint properties. And I will lay down an RBD material fracture node. I will connect it just below the RBD constraint from rules. And I will call this node RBD material fracture wall. So instead of going with the defaults, I will create my own fracturing points. So I will turn off this second level. And on the first level, I will turn off scatter points. And I will create my own scatter points based on the wall. So here under the name wall, I will add a VDB from geometry. Change the primitive type from distance VDB to fog VDB, and maybe increase the resolution a bit. So there is a fog volume, and now we can add a scatter. So let's scatter more or less 100 points. I usually like to turn off relax iterations just to make the distribution more uneven. And maybe I will like more detail here where the wrecking ball will hit. So this is to optimize the geometry. We don't want to just fracture everything with a very high detail. I will concentrate the larger amount of detail here in the center. So let's create a sphere. I'm going to center it with the wall, more or less like this. Again, create a VDB from polygons. Change the distance VDB for fog VDB. Increase the resolution and add a scatter node. So this time we want more points, probably 500 points. And we will merge these points with the previous ones. And now connect my scattered points into the fourth input of the RBD material fracture. So now on the RBD material fracture node, look for the input points option and turn it on. And there you go. Here we have our Voronoi cells. So for the final simulation, for sure I would turn on chipping and I would turn on interior detail. But for now, let's just work with this just to make sure that the simulation is faster. Now, a very important thing, notice here the Voronoi is fracturing both the wall and the plaster. And in reality, I want both of them to have different fracturing patterns. So let's make sure that under the RBD material fracture node, we select only the group for the wall object. Now for the plaster geometry, we can copy this node. So I will Control C and Control V to copy the node. I will change its name to plaster and change the group to plaster. Let's delete the wall group. And of course, we don't want the exact same distribution of points. So in fact, in the plaster, I want smaller pieces. And what I'm going to do is generate here under my original scatter points a point replicate. This will add extra points around the existing ones and change the number of point copies to 5. And finally, let's connect these new points to the fourth input of the RBD material fracture and connect the node into the main tree. Okay, so let's see what happens now. Let's press play. And a few of the pieces are breaking apart. So now we're going to take care of the constraints and the active pieces of the wall. So first of all, let's take care of the active pieces. We only want the center parts of the wall to break out, but the rest of the wall we want it to stay put. So let's lay down an RBD configure node. So this we have done before. We will connect it after the RBD material fracture. And let's change the color of this node. We will call this RBD material fracture wall. And this time we only want to affect the pieces of the wall. So let's find the group and take a look at here now. Since the wall has been fractured, we have a lot of pieces named plastered and a lot of pieces named wall. So what you can do here is under the group name, type @name, which is the attribute, equals wall and asterisk. So this asterisk will serve as a wildcard and select everything that has the name wall in it. So it will act on every single piece of the wall object. So as we did before, I will turn on the active attribute. I will also turn on use bounds, and under the properties bounding type, tick the bounding box option. So let's change the bounding box only to the area where the ball will impact. Make sure to leave some pieces on the ground. And this should work. So let's make a quick test. Select your RBD bullet solver and press play. So notice how the wall won't collapse now. Only a few pieces are breaking, but this is because the default constraints are very resistant, as we saw in the last video. So let's change that. Let's go to the RBD material fracture for the wall. Let's go to the constraints properties, and let's bring down the primary strength to 100. I will also change the properties for the plaster. So go to the constraint properties and change the primary strength to, let's say, 50. Now, another nice feature is that we can enable the color. So you can add different colors for different constraints. This will also make it easier for you to see them in the viewport. And finally, let's change the strength of the connection constraints to also 50. So remember, these yellow constraints are the ones that are holding the plaster to the wall pieces. So let's change the name of the node as well to connections. And let's take a look now. Let's look through the camera and see how our simulation is turning out. And I think this is looking quite fine.